Okay, welcome to lecture number 46. We will learn few more theorems related to circle in this particular lecture. Before that, let us write the definition of tangent. When do we call a line tangent to the circle? So by definition, if a line and a circle has got exactly one point in common, then the circle is tangent to the line or line is tangent to the circle. That is how we will understand any line being tangent. So there are three cases. A line can be intersecting circle into distinct points. Line can be such that the circle is not intersected at all. And the third position is basically when the line and circle are intersecting, but both the points of intersection are coincident. There are 2 points of intersection. They are coincident at this point, and then therefore we call that line as tangent. So by definition, the line is a tangent to the circle if it has got exactly only one point in common. So if this is the definition of tangent, then we have a theorem that to a circle, if we draw any radius and draw a line which is perpendicular to this radius, this line L is perpendicular to radius segment, say MA, then that line is tangent to the circle. So if we want to prove this particular theorem, what do we need to show? That if we take any other point on the line, say let P be any other point on the line, and we join PM, we show that the radius, the distance PM is greater than the radius of the circle, and circle is locus of all the points equidistant from fixed point. In this case, the fixed point is M, and therefore circle has all the points equidistant from M, and P is the point which is at larger distance compared to the radius of the circle, and hence it will not lie on the circle. So we have to prove basically MP, distance MP for any point P on this line other than A is always going to be greater than MA. And again, the proof of this is very simple. We have to use Pythagoras theorem. Pythagoras theorem says this is a right angle triangle, therefore MP square is equal to MA square plus AP square, and all the quantities are positive, all of them are segments. Therefore, unless we add some positive real number to MA square, we don't get MP square. Therefore, MP square is greater than MA square, and hence MP is greater than MA. That is how we prove it, that if you take any point on the tangent, it is going to be at higher distance, more distance compared to the radius of the circle. Okay. Now, is this going to be true in case we consider the converse? So if L is tangent, then it's perpendicular to MA, that is radius segment. It is perpendicular to radius segment at that point, at the point of contact. Okay, here this is converse of the first proof, and we will prove it. Suppose line L is said to be tangent to the circle at point A, and center of the circle is somewhere else, that is M. Suppose center is here M, and if we join MA, we want to show that it is perpendicular, but suppose MA is not perpendicular to L. If possible, MA is not perpendicular, and in that case what we can do is, we can always draw perpendicular to L. Let this point be B. It is indirect proof. Suppose MA is not perpendicular, then we can always draw perpendicular from M on any line. So we have drawn perpendicular, which is MB. Now what we do is, we copy this AB over other side to get C. This is congruent to this, and then we join AC. Now without drawing circle we will prove this. Basically MA is not perpendicular, therefore we have another segment which is MB, which is perpendicular. We copied AB to the other side to get BC. We joined MC. Now you see AB is congruent to BC. Construction. Angle MBA is congruent to angle MBC, is equal to 90, and MB is common to both. Okay, therefore by which theorem these two triangles are congruent? It is by SAS. SAS, triangle MBA congruent triangle MBC, which gives us MA equals MC by CSCT. So if M is the center of the circle and A was the point of contact of line L with circle, and if possible it is not perpendicular, then we end up getting one more point C on the circle because it is equidistant from M, same as MA is equal to MC. Therefore we end up having 2 points on L, A and C, which are equidistant from center. Contradiction to definition of tangent. Tangent is said to be having exactly 1 point in common with circle, and therefore if we start otherwise, then if it is not perpendicular we get contradiction, right? Therefore this is the second theorem, which is called the obvious necessary condition in this case is sufficient for proving converse. Next result in this particular lecture is basically, if we have a circle, if we have a tangent, and if we have a secant, notation, this point is A, let this point be B, let this point be Q, let this point be B, and if there is any other point X here, this is circle S, another point anywhere point here Y, and this is line L, this is line T, tangent and secant. So in this situation, this is called tangent secant theorem. Tangent secant theorem. What is to be proved? If this is the situation, tangent is tangent at A, from A only another secant is going, then angle BAP, angle BXA. This is to be proved. Now this is easy. I request all of you to pause this video and check whether you can do this proof independently or not. Else watch our videos. It is simple. Join, whenever you are dealing with circle, join the center with the points which are important to you and mention the radius. These two are very important things for the circle. Suppose this angle is x, then this angle will be 2x. Central angle is 2 times that of angle at circumference. Now this angle will be 180 minus 2x upon 2, which is 90 minus x. This also will be 90 minus x, right? And when you join center M with A, the theorem that we have proved that the tangent is supposed to be perpendicular, and out of that 90 minus x angle is taken here, therefore this angle must be equal to x. So x is equal to x. This is what is the proof of tangent secant theorem. You just chase few angles and you get it. Okay. Now how do we write the converse of tangent secant theorem? Suppose there is a line, suppose there is another line, both of them intersect at A, there is another angle which is x, this point is B, and suppose it is given that this angle x is equal to this angle x, then the converse of tangent secant theorem says there exists a circle passing through AB and X which should be tangent to line PQ. Okay, so again you can try this converse also independently, but if you don't get it, you can watch this. If possible, this line is not tangent, and therefore we draw a circle, and if possible this line is not tangent, therefore you draw another tangent. Okay. another tangent, the moment you draw at point A, we have our tangent secant theorem saying that this angle also must be x. Suppose this point is P dash. So by previously proved theorem, we get measure angle BAP dash is equal to x, but it is given that measure angle BAP is equal to x. Therefore P coincides P dash, or not P coincides P dash, they can be different points. Basically the line PQ and the line P dash Q dash must be same. This implies PQ, line PQ coincides line P dash Q dash. Okay, so this is converse of tangent secant theorem. These two theorems are important when you have advanced problems, and if you suddenly apply converse of tangent secant theorem or tangent secant theorem, the difficulty level of the problem substantially comes down. So I request you understand and learn the proof of these two theorems independently. You should be able to prove them anytime. Let us see application of tangent secant theorem. In application, we have basically a circle and a tangent, and there is a secant now which cuts the circle in 2 points. Let this be P, let this be T, let this be A, let this be B. We are supposed to prove PA into PB is equal to PT square, right? Now again, this is something similar to PA PB is equal to PCPD. Here we draw these two lines and we use our simple technique of proving ratios. PA upon PT should be equal to PT upon PB. So to prove that, that is to prove that, and therefore now I will look at triangle APT, whether it is similar to triangle TPB. If they are similar, then I get this. If I get this, I get this. So APT, is it similar to TPB? So angle P is common in both, and just now we have learned that this angle X is equal to this angle X. Therefore these two triangles are congruent by tangent secant theorem, and hence you end up getting PAPB is equal to PT square. The last activity in this is basically you have a circle and there are two secants, two chords which intersect each other at P. This is A, this is C, this is B, and this is D. Suppose measure of angle AFC, measure of arc AFC is Y, this arc is Y, and this arc is measure is Y, measure of this arc is say X. Then we are supposed to find out what is the measure of this angle BPD, this angle. Okay, again this problem is simple problem. When we say measure of arc is Y, its central angle is 2y, and its central angle is 2y, and therefore if we suppose now what we should do is we should join some arc giving us this value equal to y by 2, and this will be x by 2 because this is inscribed angle here, and therefore this angle, which is exterior angle of a PDC, will be x plus y by 2. Similarly, there is one more problem. If we have a circle and there are two secants, again AFC is equal to y, this arc measure is y, this arc measure is x, then what is the measure of this angle is asked. Again we have to create inscribed angles using these arcs. So if we join one of the two chords, then this is y by 2, this will be x by 2, right? And therefore measure of this will be x minus y by 2 by exterior angle theorem. So by exterior angle theorem we prove this. So this is what was our lecture number 46. The homework problems are given in lecture number 45. For 46 you should solve them. Thank you for watching lecture number 46. See you in lecture number 47. Thank you.